Let's thank the weekend. All right, next speaker is Alyssa Bullock, the Brick Line Survey in 2024.
Hi, everybody. My name is Alyssa, as you know, and I haven't given a symposium talk for 2 years. The last time I gave a symposium talk was 2022, and then I gave my candidacy talk last year. So forgive me if I'm a little low on background information. I forgot we were supposed to do that, but I'm very thankful that Desmond went before me because he sort of introduced stuff about molecules and chemistry, which is what I'm going to talk about in this presentation. So the last time you heard from me talking about this thing called the brick, I realize there's first years here who maybe don't know anything about my project. I'm studying a different cloud in the galactic center. This one much less actively star forming than Sagittarius B2, which is what Desmond mentioned earlier. Basically we have this wide band spectral line survey with the ALMA interferometer, and we're trying to answer questions of like, you know, which molecules in our wideband line survey trace like what processes related to star formation. We're focused on one particular protostar, which is not visible in this image, and sort of the diffuse environment around it. So I published a paper in fall 2023 using just a little bit of data from this survey because we discovered this line of the molecule methanol, which Desmond also mentioned, undergoing this thing called dazing, which is like anti-mazing. I don't want to talk about that because I talked about it last year, but I'm bringing this up because basically in order to determine, you know, what's the difference between the core versus diffuse gas around the core, we need a model, like a footprint for where the diffuse gas is. And we chose, so this is a map of the molecule methanol dazing, and that represents a very dense area in this region. So we chose a particular region within it, and we named it the frown in contrast with the core, because it looks like a frown. It also kind of looks like ditto, but if you melted. And in particular, we're taking the mouth of the frown. So that's the area that we're contrasting with the core. Okay, so what have I done since I published that paper? I made continuum images from all of our bandwidth that we have, which I'll show you in a bit. I went through and did some line cataloging, or really more like molecule cataloging, which I've been doing for the past like 4 years plus of my PhD. I wrote an ALMA proposal, really renewed an ALMA proposal, didn't get through, typical. I did some observing for a related project at the GPT using the Mustang 2 instrument, and I also gave a colloquium at Green Bank. And then I did line cataloging again, but this time with like consistency and improved procedures that got me, you know, upper limits, better answers than before. Went to a workshop on ACEs. Maybe I completed the molecule catalog. That would be cool. It's kind of true. So yeah, great. I'm going to focus mostly on these things, which is the continuum imaging, which I'll show you first, and then I'll show you the procedures that I did to make the line cataloging better, and then I'll show you the results. Okay, continuum images. Basically, this will give you context of like the area that I'm looking at. So that thing in the middle is a core. It was originally identified as a water maser. It's a continuum source in our data. But we can see that, you know, maybe in 10 years ago or so, when this area was first imaged, we didn't know that there was all the substructure around this core. But in fact, there is a lot of substructure. In particular, there's a lot of, well, the laser doesn't work, it's fine. A lot of like cores, both close into the core nearby and also like off to the side. So this is a continuum image made from the bottom of band 3, or sort of like the middle. This is one slightly higher frequency, even higher into band 4, and then this is our band 6 continuum image, which I had to make at a different scale. We used a special method of continuum imaging called multi-term multi-frequency synthesis, which you have to use if you have a super wide bandwidth, because the relationship between the spatial structure and the spectral structure changes a lot over the bandwidth that you're imaging. So you have to use this special Taylor series-based method. So we did that and got some continuum images. Now we have cores identified where we can measure different molecular contents, maybe from the central core. Okay, pretty images. That'll be all the images in this talk. So in February of 2024, I didn't have a catalog done. I had written in my notes, do SIO, which is a molecule, next, then do the rest of the molecules. that's a funny joke because now it's whatever, November, and I'd only just finished the catalog. So the initial catalog. So here's the name of the code that I made that like wraps all the stuff that I've been doing for the past several years into one thing. Basically, it's code that pulls from different molecular catalogs. It can pick out any molecule you want and make an LTE model of that molecule. You can compare your model to data either extracted from a core or a region, depending on what file you provided. And you can also pick which lines of the molecule that you want it to show, you know, based on what kind of excitation conditions you expect to be in the region. And yeah, here's an example plot of what the output of this code is for the molecule CS. Basically, it's like, okay, here's 3 lines from CS. And I added some like convenience things so that you can make rotational diagrams to try to find out good temperature fits. But all the fitting that I've done so far for molecules has been by eye, messing with model temperatures and model column densities and velocities and stuff. And that resulted in initial molecular inventories of the core and the frown with initial LTE model fits that I haven't done any like error measurements on. So this is a plot that shows every molecule that I could think of. If you can think of one that's not on here, please tell me. So this is like all the molecules plotting their column density with respect to methanol, which is a thing that we normalize over, or normalize by rather. So this also, the blue is a little hard to see, sorted by increasing column density in the core. The frown is orange, and this is also compared to Desmond's data for the molecules, which we have data from, and also W51, which is another star forming region that Taewal will be talking about later. Yeah, so we can already like do some science here. We can see comparing the core and the frown, there's a lot of molecules that are much brighter in the frown than the core, which is great. That means they might be diffuse gas tracers or dense gas tracers, rather than core tracers or tracers of like infall or whatever. So that's cool. Just zooming in on some complex organic molecules, which may be of interest to people. We can also do more comparison with other star forming regions that are in contrast to the brick, which is relatively quiescent. So SAGB2N, which is in the northern part of SAGB2, which Nazar will talk about later. We've compared the molecular inventories we have there. This is also column density normalized to methanol. And yeah, these are plots that will go in the paper. Basically, I still have to do a lot of finagling of like making sure that every single line is identified, and that all of the temperatures and stuff match up, but that will be like in the future. So as I was going through this, I was like, yeah, this is going great. Everything's fine and in LTE. Well, it turns out that some molecules don't behave CS, SiO, SO, PN, which is a cool molecule, and also methanol. Turns out that they're subthermally excited, which means that we have to do non-LTE modeling at some point. However, that will probably not go in this paper because there's already going to be a lot in this paper. So in addition to the plots that I showed you, in the analysis section will be one giant spectrum of all of our data with one giant model that explains all of the different molecules in that spectrum, along with LTE modeling results for each molecule that I put into the code. And also a list of unidentified lines, if there are any. Probably there will be. Also, we can do science with the measurements in the analysis section. So basically, every molecule we can measure something with. Just from the column densities, we can get abundance constraints on each of the molecules in the core versus the frown. We can use particular combinations of molecules, say SO and SO2, to derive the chemical history of the cores. Thanks. And yeah, we can get isotope ratios, et cetera. And also, one cool thing that we can do is measure the X factors or relationship between integrated intensity, or just like how much stuff there is, versus the column density fit from LTE, to try to see, is it the same in the core versus the frown? If so, might mean that the brick has a consistent X factor. If not, we don't know what that means. So this is all non-trivial, but at least it's breakable into parts. Stuff that's not going to be in the paper, inventories for the other cores, because that seems like too much for one paper. Also, we're maybe not going to do non-LTE modeling. And there's always going to be other stuff we find that we don't have time to include in the paper. All right, I hope you enjoyed this whirlwind tour of the brick. Thank you for your time.
Any questions? Yes.
So methanol, I guess I'd say is one of like the simplest, as Desmond said, one of the simplest complex organic molecules. It's relatively abundant and it's good to normalize both stuff that is more abundant than it and also less abundant because it's kind of in the middle. That's what I would say. Thanks.
Any other questions?
You said the fitting is all without error bars. Did you mean like you don't have observational error bars on the data when you do the fitting?
I do, I just haven't incorporated them yet. So by error bars, what we'll probably end up doing is like for each point calculating the difference between the data and the model and then incorporating that into the fit of the temperature and column density combo for the model. But yeah, basically we don't have observational error bars on the spectra, do we? I don't think so.
You can get those.
I mean, we can like
Yeah.
say, 5% error, 10% error, whatever, but
You also said the fitting is I you worry that there could be multiple solutions where or is it the lines are all really distinct from each other? So you can say, oh, okay, the same molecule I could fit this line and this with this amplitude.
that's a great question. I absolutely do worry that there are multiple solutions. Even for a single molecule, multiple temperatures often work. And, column density is just like, makes everything go up and down. So I think that doing all the different, like the giant model with all the molecules together and seeing all the different lines of each molecule all working together, that will help us sort of remove some of that degeneracy. But we can also use like prior knowledge of, do we really expect this molecule to be more abundant than this molecule? But yeah, that's definitely something that I'm sort of working with. Thank you.
Time for one more question.